right, I think it's about time to start. So, to everybody, welcome. Today's topic is meeting the plasma challenges in the semiconductor industry. My name is Thomas Gilmore, and this talk should last about 50 minutes, and then there's going to be a Q&A session at the end. You may notice there's a Q&A section, like a tab that you can access in Zoom. Please type your questions in there, your comments in there. And at the end of the presentation, I'll open it up, read through it, and answer whatever I can. Let's get going. I'm just going to turn off my camera to conserve a bit of bandwidth, and then we'll get started. Okay, let's go. So just a quick bio for those of you who don't know me. I'm a plasma physicist. I've been working with plasma physics in that field for about 15 years. And I was Impedance's first field engineer. So I have quite a lot of experience using our products with clients around the world in all sorts of different applications. And at the moment, my job is to work closely with the CTO and with customers to make sure the right plasma diagnostics meet the new semiconductor demands. And this talk is somewhat about what are the demands of the semiconductor industry. Quick intro to Impedance. So Impedance is based in Dublin, Ireland. We were founded in 2004. We have more than 40 employees, and we also have a global distribution network. So we have distributors throughout Asia, for example. And our core focus is to provide advanced plasma and RF diagnostic equipment, in particular to the semiconductor industry. Now, we don't just serve the semiconductor industry, we also service university and research markets and the sub-suppliers of the semiconductor industry and so on. So let me give you an outline of what today's talk will be about. I'm going to try to go through the different challenges in the semiconductor industry, starting from a very, very high level and going from there. But, you know, the challenges are very, very broad for the semiconductor industry, but we're going to focus in particular on challenges relating to plasma surface interactions, okay? This is where my knowledge comes in and where Impedance's knowledge comes in. And throughout this, we'll mention some measurement solutions, some impedance sensors, and I'm going to try to give as many practical data examples as possible. Let's go through it. So what are the challenges in the semiconductor industry? Okay. So I want to start very high level. There is actually a kind of looming energy crisis related to the semiconductor industry. This is something that not many members of the public realize. But semiconductor, based equipment. So I'm going to just label it as, information communication technology. It's estimated to use over 20% of global energy by 2030. So in other words, all of our computers, our laptops, our data centers, our mobile phones, our smart devices, our cars, whatever, this is going to use a really huge amount. This is like a really huge part of global energy demand. You can kind of subdivide this into memory and computing. So with memory, at the moment, globally, data centers account for 2 to 3% of energy usage. And in fact, here in Ireland, it's something like more than 25% of energy usage already. And this is forecast to grow 4x by 2030. Okay, so this is significant. And then there's also demands on computing, right? So due to, say, for example, the recent growth in AI applications, the most recent estimate is that computing demand is going to double every 6 months from this point on. So, we talk about Moore's law and, the doubling of computational power and so on, but even demand itself is going to be growing very, very rapidly. And this is quite a challenge, considering the global issues regarding using so much energy. So the challenge that has to be met, memory stored per watt must decrease by a factor of about 1,000. And similarly, the CPU energy usage must massively decrease. So this means new gate designs, new materials are needed, and all of this results in new challenges in plasma control. So let's go further into that then. So new gate designs are emerging to meet these challenges. You may be aware of the concept of nanosheets, these gate all-around transistors, fork sheets, and so on. And these would bring us down to the 2 nanometer to 0.7 nanometer feature sizes. And here's kind of a diagram showing this going into the future. In general, the concepts are quite simple. Like if you think of why we're making smaller things and why we're going in this direction, from a high-level physics concept, it's the idea is you want to lower the resistance from the gate, so you lower the power usage. Also be a bit smarter with how you do power delivery. This is called backside power delivery network. And also you want to change the capacitance so you get faster speeds. So all this results in new gate designs to do these simple concepts. Also, I would highly recommend, so it's a bit about out of the scope of this talk, but if you want to know a lot more details about these gate designs and the future of these things, IMEC have published a lot of material on the future roadmap. So I would highly recommend reading that. So let's talk about plasma-assisted processes. In general, as you've seen in the diagram in the last image, the trends are as follows. We want smaller dimensions. We want these, these gate all-around things. This means that these are 3D structures, okay? Which means that, there's gaps and there's valleys and there's areas that are much more difficult to reach with standard, let's call it 2D semiconductor processing. There's also new materials. New materials leads to new challenges in selectivity, right? So you want to make sure that your process can etch the correct material and depth the correct material and so on. If we look at the how do you make these things? Almost everything is a plasma process, whether it's in deposition and all the different flavors of deposition that exist, or lithography. There's electron beams and there's other things that would relate to charged particles. In etching, obviously wet chemical plasma is not related to, but reactive ion etching and ion beam epitaxy and all this sort of stuff, plasmas are highly related to this. Okay, they're driving the processes. So the challenges to do these gate designs and the challenges to do these, they're all going to come back to the fundamental challenges with plasma monitoring. Okay, so let's have a look then specifically at the fabrication challenges. All right. So, we want better control over the processes, which is a whole topic on itself. We want higher throughputs. So that's another challenge. We want atomic scale precision, right? So atomic layer deposition and etching has its own set of challenges compared to dielectric etching or metal deposition. Uniformity is the classic challenge. We know that. I mentioned higher selectivity. But some of the kind of newer problems, going to higher and higher and higher aspect ratios. So I'll show a diagram in a moment to explain what I mean by higher aspect ratios. But the idea is we have deeper and deeper trenches. We need to be, etching. We need ions to be going straight down. We also, when we're dealing with atomic layer etching and deposition, we can be dealing with more sensitive materials. We want to look at lower damage. So again, plasma control is needed to meet these fabrication challenges. So if we look at this at a high level, we're looking at real-time control needs. We also have needs on the equipment development side. So new equipment is going to need to be developed to meet these challenges. And also, of course, model validation. So a lot of computer modeling is done when developing these processes and these tools, but we need to validate that as well. Okay. So just highlighting here for this talk, we need to be able to do measurements of charged and neutral particle densities and fluxes to the surface. And we need to also look at the energy being delivered to the surface of charged and of neutral species. Okay. So, and these things have been measured for a long time, but now it's getting harder and harder. Okay. So let's go into plasma surface interactions. So in order to understand the challenges. So if we just zoom into the surface, there's obviously quite a lot going on. There's sputtering happening, there's depositing happening, there's etching happening. There's all sorts of different processes, some of them driven by charged particles, some of them driven by neutrals, some of them driven by reactions. Okay, so it's quite a mess on the surface, but we have to understand every one of these components. Okay, so what are the challenges? So these are the ones that I'm going to focus in on today. We must know what our ions are doing. We must know the ion energy. It must be high enough to etch or low enough not to damage the surface. Okay, this is quite obvious. Etch rate is a function of energy. So that's the first thing to keep in mind. And the dep rate is also influenced by ion energies. So local ions can be, even in a deposition process, if there's ions locally, they can be contributing to the deposition or they can actually be etching depending on their energy. So we'll go into some more specific examples of that later. The ion flux must be controllable and monitorable to improve throughput, okay? Because obviously etch and dep rate are a function of ion flux, okay? So if you can, um, if you have a higher flux, you can do your process faster, you got higher throughput. But that also means you have to have very precise control. You don't want a really high ion flux, but your process has to be 1.2 seconds long exactly, right? That's not going to work. So this is the next challenge. The two that are kind of newer are we need to have more information about the ion angular distribution. Okay, so if we're doing these deep etching, these high aspect ratio things, the ion angular spread, I'm going to just kind of give a number here. The ion angular spread can't be more than this. Okay, so the arctan of the critical dimension divided by the trench depth. Or in other words, if you have a trench which is 100 to 1 aspect ratio, or 200 to 1, or 400 to 1, this would be the arctan of 1 over that number. Okay, this gives you the ion angular spread, which is allowed. And then there's also this non-charged etching. So not just chemical etching, but radical etching. That's a new challenge. How do we measure and tune radical etch rates? Or maybe, I mean, people already do this, but maybe a better question is, how do we do this without using product? Are there instruments that exist that can help us give insights into this? So I want to try to touch on all these topics in detail in this talk. Just let's go back to the basics for a moment. I'm not sure who's in the audience, but it's always good to start the basics. So ion energy is essentially the ion velocity when an ion hits the surface. The velocity will depend on the mass, of course. And if you're on a grounded electrode, the ion energy is going to be about the same as the plasma potential, because the acceleration is due to the voltage difference between the plasma and the ground. Okay, quite simple. For an RF bias electrode, it's more different. Much higher energies are achieved even with low powers. This will be power dependent, frequency dependent, geometry dependent. This is fairly complex. Okay. And then ion flux is just how many ions per second hit the surface. So how quickly the process is done. Might be worth noting that some people care about ion dose, so the flux times time for their processes. This is essentially to do with the thickness of whatever's being produced in the end. And as mentioned, the actual value of the energies matter. Too high, it can damage the material. Too low, it's not doing its job, functionalizing the surface or something. And in a typical chamber, power fluctuations, maybe matchbox heating up or something like that, can change all these values mid-process. So it's not great. I want to just show you this diagram. For those of you who haven't seen it before, this is a nice diagram by Andre Anders in this paper here. If anyone wants a paper, I can send it on. But this is an attempt to make an intuitive diagram for understanding how temperature and how the energy delivered to the surface by ions impacts the resulting materials that you get. So the grain structure, for example, the crystallinity. And there's obviously a temperature axis. So things depend, some processes you have to run hot, some processes you can run cool. But the axis I'm more interested in is this one here with energy labeled here. So energy delivered is pretty much to do with the ion energy and the ion flux over time. Okay, so you can see time on this axis. And the higher the combination, at some point, so you can see here, when ions are above a certain level, this is material dependent, of course, but above a certain energy, they start etching instead of depositing. And below that energy, they can etch a little bit, so you don't get the same thickness as you would. It's not like net deposition. And then when the energy is low enough, you get more deposition. So just keep this in mind, that the ion energy and the ion flux matters, as well as the temperature, not just for how quickly or how slowly a material forms, but what material forms. Okay, like the difference between amorphous and silicon crystal. Amorphous and crystalline silicon will depend on these sort of parameters as well. Let me give you some just practical examples here. So here, this is ion energy versus gallium nitride etch rates. This is by this group here, so this is the tool layout. So it's an ICP tool, and you have the sensor down here, and you have the coupon down here. And what I wanted to show you is, if you look at the etch rate versus the self-bias voltage. Now, self-bias voltage is not quite ion energy, but it's pretty much the same idea. What you're missing here is plasma potential to get the ion energy. But in any way, the concept is that there's some point at which you start etching the materials when the ion energy is high enough, and then it starts increasing with that. So this is something you need to understand for whatever material is in your chamber. Okay. Surface roughness also depends on the self-bias. That can change depending on that as well. Okay. This is again related to the diagram in the previous example. Now, this here is kind of like an average energy, but in reality, in this chamber, the energy looks something like this. So you get these ion energy distribution functions. And depending on the bias, that shifts the ion energy distribution function. We'll go into more of this a little later. One other practical example, just to show you this. This is for silicon or Si3 and 4. You get the same idea. There's some cutoff energy, and then once you go above that, you start etching. Okay. So message here is not only does the ion flux matter, but the ion energy matters. And both of those can drift in a process. So that gives us challenges in process control. Okay. So let's just talk about a practical example of a recipe, because, the processing of materials is not, modern processes are obviously quite complicated. So you have your incoming material, which will have some sort of mask and some sort of material you want to etch in. So this is an example of high aspect ratio etching. And then you apply different powers, pressures, gases, different chemical flows, different molecules, depending on what you're etching. You may be changing pulse frequency, duty cycle, temperatures, and so on. And usually when you do this, you have some sort of target. So I mentioned earlier on, like this is the CD critical dimension, this is the depth. So this will have a certain aspect ratio. So here, this might be 20 to 1 or something like that. This is the target. But if the process is not quite finely tuned, you can get all sorts of different results here. So the top is closed, or it's bowing, and there's also other effects, like you get notches down below, or you don't get deep enough. So we really need to understand everything that's going on with regards to the ions and the neutrals in this case, in order to achieve these target profiles. So again, just keep in mind that if you want to etch something down here, the ion cannot be at an angle more than arctan of CD over depth. Okay, so that could mean that for like a 200 to 1 aspect ratio, any ions greater than 0.3 degrees with respect to the normal of the surface, like any ions more than that are going to collide with the walls before they hit the bottom, and there will be ion angular spread. And in fact, the change as we go down here, like there's effectively, I'll show you some data a little later, but when you're looking at a situation like this, you actually have an etch rate as a function of depth due to the ion angular spread. So that's something we need to measure. I want to do a quick aside on one other challenge for the semiconductor industry very quickly. Look at these gases here, C4F6, C4F8, and other fluorocarbons. There is an environmental concern. So I mentioned the IMEC tech roadmap, but if you also look at the tech roadmaps announced by, say, the semiconductor tool manufacturers, they often bring in the environmental concern of these tools. So obviously, these CF gases are quite critical for etching, but they're quite environmentally damaging. So if you look over here at the global warming potential, CO2 has a potential of 1, but like SF6 is 23,000, CF4 is over 7,000, C4F8 is 10,000. So they're really very environmentally harmful, and we do want to get away from them where possible. I will mention, I tended to talk earlier this year, Air Liquide are trying to develop materials that do the same etching, but they have much smaller GWPs, global warming potentials. So if you're interested in the environmental concerns, maybe contact them. And they mentioned these two chemicals, Tonga and Macran, which are replacements for these, and also play with the ratios here. So these CF ratios actually impact what kind of profile you get in here. They try to tailor it so that you get these particular profiles with the mix that you get. So just be aware that they exist. I won't go into depth into this, but one other way of reducing this impact is by running some processes cryogenically. Now, strictly cryogenic is like minus 200 Celsius and below. But processes are being developed in the sort of minus 30 Celsius, minus 40 Celsius, which really help again with this sort of straight line etching going straight down. They tend to use less power, and they have they use less damaging gases. So maybe look into that if you haven't already. Cryogenic processes may be a way to go. Okay, so just going back to this topic. So ion energy is controlled through a combination of effectively the electrode bias and the plasma potential. They're the two key drivers. Okay, and the electrode bias is not linear with bias power. Similarly, the ion flux is linked to the ion energy. So as you apply different powers, you could be changing the plasma potential or changing the electrode bias. Okay, so but you're also changing the density. Like when you're changing the density, you can also be changing these two parameters. So this is typically linked. So we have to talk about how do we separate these? How can we have independent control over these two things? And there's a number of different solutions to that. The kind of oldest existing ones will be different chamber configurations. I'll mention some in a moment. And different frequency configurations. Okay, so using higher frequencies or lower frequencies can be used to separate these. But I also want to mention pulsed RF or pulsed DC, so doing power modulation for doing control. And I also want to talk about tailored waveform and show a number of published examples on how this can help also do very fine independent control of ion energy and ion flux. Before going into this, let's go back to the basics for a moment. So for those of you who haven't seen ion energy measurements before, here's the simplest example where you have some plasma at plasma potential Vp. You have some electrode at an electrode potential, but let's assume that it's grounded, so it's zero. That means the ion energy, which is what it picks up as it crosses the sheath, is going to be the difference between the plasma potential and the electrode potential. Okay, so if it's a grounded situation, it is literally just, if the plasma potential is 20 volts, then the average ion energy is going to be about 20 eV. Okay, and if you have some DC bias applied, it's the same idea. It's just a difference between the two voltages is going to give you information on the energy. Now there can be spread in the energy due to collisions. And due to temperature and so on, but this is kind of a typical ion energy distribution. So energy is on this axis. It's the black line you look at. So we have all the ions around some peak value, and then there's some maximum energy at this point, and then we got no ions again. Okay. If you apply an RF bias, it's a bit more complex. So the idea is you have a varying electrode bias, which is plotted in this diagram. The red line here is the electrode potential. The blue line is the plasma potential, which doesn't stay constant, actually. The plasma potential will also oscillate with the applied bias. And then sometimes the difference between the plasma potential and the electrode potential is small, and sometimes it's very large. So the result of this is some ion energy distribution function, usually with some peak splitting. The splitting depends on, the mass of the ions involved and the frequency involved, like how much can the ions respond to the applied voltages. Like if they're too heavy, they're basically going to see an average bias. But if they're lighter or if the frequency is slow enough, they will follow along this voltage and you get wider peak splitting. So this is a typical distribution that you see there. So you see much higher energies. In this going up to say 300 eV, you have peak splitting, and then you also have these additional peaks down here are to do with charge exchange collisions in the sheath. Okay. So how do we then separate out ion energy and ion flux? So I mentioned that changing the tool configuration is an easy way. Here's some typical chamber design. So you could change the you can change where you apply the power. Okay, so if you apply power only to the top electrode and you have nothing on the bottom, you're effectively just going to change the plasma density and you're going to slightly change the plasma potential. I'll show you some real data in a moment, but this is one way of increasing depth rate or decreasing depth rate can be used just by playing with the power on the top. If you play with the power on the bottom, this will, you're going to link your ion energy and your ion flux. The higher the power you apply, the more plasma density you get, but also you get much higher energies. Okay, so so one solution is to do both. You can apply RF to the top and to the bottom, and use the bottom to control energies and the top to control density. Right, it's fairly straightforward. This is typical ICP tools. You have the plasma almost separated from where you have the substrate, and you carefully apply biases, and you carefully apply different powers to the top in order to change your process rate. Another method is by applying more than one RF bias to the substrate. Okay, so you could apply a low frequency and a high frequency. The low frequencies elicit more response from the ions, so you can get much higher energies, whereas the high frequency is mainly delivering, plasma density. So that somewhat separates them out, although it's more complicated to build a tool that way. So let me just show you some practical examples here. So this is one where you have IEDF, where you're changing the top electrode. Well, in this case, it's an ICP, but you can see here, like at 50 watts, you have this little thing. So as you raise the power, you raise the ion flux. So the area under this curve is the ion flux. So as you increase the power, you can see the ion flux increases a lot, which is what you expect. The ion energy does not increase that much. Okay, I'll show a diagram in a minute to show how these vary versus power. Then if you apply different powers at the bottom, in this case, when there's 0 watts at the bottom and power applied at the top, you get this peak at the plasma potential, and you have a little tail due to collisions. And as you increase the bias power, you get higher and higher energies. But you can see here, it's not so linear. Like the power goes like 0 to 4 to 10, 30 to 60. It's not linear. Similarly, the peak splitting changes as a function of power. Okay, so that's another problem. So, I mentioned earlier the etch rate is a function of ion energy. So now you have a big wide spread of ion energies, all of which have different etch rates. Okay. Also note the sensitivity of power going from 0 to 4 watts. So from a floating potential to a small bit of power can have a large change. Okay, so small variations in power can cause fairly large changes in the ion energies. Okay, which could take you from etching into not etching, or take you to a different mode dealing with the materials. So this is where the issues start arising in, when you're running a tool for months in a row and you have to do maintenance. It's in part to solve these sort of issues. Let me just show you practical examples of the different frequencies. This will be important later for the tailored waveform and so on. As you apply higher frequencies, the ions react less, but as you apply lower frequencies, the ions react more. So with the same power, you get actually much higher energies. Okay, so in this case, all of them have the same power, but you get different responses with the different frequencies. The responses aren't always as clear as this. So in a magnetron sputtering system here, the responses are really quite unusual per frequency. Okay. If you go back to CW plasmas, if you look here, here is ion flux versus an ion energy at different frequencies, and you can see again, there is a relationship between the two, like they're both linked in tools, and you can see here again, in this case, increasing power increases the energy more. In this case, increasing power increases flux more. So using different frequencies helps, but it is not linear. Okay. So let's go forward. So we do need independent control, and that means we're going to have to do new techniques. So let's talk a bit about pulsed RF. So I'm going to show some data actually by one of our attendees of the call at the moment. So this is work done by Gilles Conche in CEA Leti, where they were looking at ions response to pulsed plasmas. There's a talk by him on actually the Impedance YouTube channel. A talk from a number of years ago is there. So the idea is, what is pulsed RF? So previously we were applying a single frequency continuously. So we had 50 watts to say 13.56 megahertz all the time. And if you go to pulsed RF, the idea is the power is on and then it's off. It can also be multi-level, and it doesn't even have to be 2 states, it can be many states, but for now, let's just keep it simple with on-off. And this gives you some advantages. It actually allows you to apply much more power in order to achieve higher energies, but without massively increasing the amount of energy you deposit in the tool. So you can imagine if you're trying to reach, like if you go back one more time to this diagram, if you increase, like, if you want to increase energy, it kind of goes with pretty much the square root of the power. So in order to double the energy, you have to go 4 times the power, and eventually gets to the point where it's just a really unusable amount of power being delivered to the tool to get the ion energy you get. But by pulsing, you can apply the large powers, but you can decrease the average power that's being applied to the tool. Okay, so it's more manageable. There are also other benefits to pulsed RF. The same concept is used in high PIMs. So if you're familiar with high PIMs, you have a really, really short on time, like microseconds, tens of microseconds, with really, really high powers to get a really maximum ionization fraction. And then the plasma is off for a long amount of time. So the average power applied to the electrode is reasonable, but the instantaneous power can be really large. When you look at the ion energy distribution function in this case, you basically get the sum, like you basically see the distribution function for when the ORF is on and when the ORF is off. So here's the case where it's on, so you have some amount of power, and then in the off period, you see ions from the afterglow. So the plasma potential is dropping rapidly, so you get very low energy ions. Okay, so this is typical. You get these different levels. Just some practical examples. If you increase the duty cycle, you increase the flux, because obviously the larger the duty cycle, the more the plasma is on, so the more ions you get. And if we go down here, so higher duty cycle is higher flux. One thing to note is that, pulsed RF is quite complicated because the plasma has to strike and it also decays, and how it does that is very, very gas dependent. So if you're using argon or something, it's straightforward, but if you're using molecules, the molecules actually go through different chemical states. Like, what I mean is, a molecule has like rotational states, vibrational states, dissociation states, and as energy is being delivered, as the power comes on, it has to go through all these different modes. So you can actually have a really chemically dynamic plasma when you're pulsing. In fact, certain reactions take a minimum amount of time. So by changing the pulsing frequency, you can actually control what species form and what don't. Okay. Yeah. Here's another example. So how does that impact ion energies as well? What happens to ion energies as you're doing pulsing? As you change the duty cycle, you change the ion energy. The smaller the duty cycle, the larger the energy. Okay, so you can use this to achieve quite high energies if you wish. Again, you can think about this as you can be delivering more instantaneous power. But actually, let me give you a kind of overview here. Why, for example, a 5x reduction in duty cycle causes a 5x increase in energy. And the way you should think about it is, power is voltage times current. So if with smaller duty cycles, you're getting less current, so for the same power, there's going to be a higher voltage. So you're going to get higher energy ions. So this is kind of trying to give an intuitive way of how to think about that. So this gives you a new thing to play with. You have power, but then by changing how much the power is on, you can change what flux you have and what energy you have. So this gives you a new form of control. This is actually from a recent publication, and let's bring it back to actual critical dimensions. Again, I can share this paper if anyone wants it. But playing with pulsing cannot just be done on the bottom electrode, it can be done on the top electrode. So by playing with how those are pulsed, in sync or not in sync, you can actually change what profiles you get out at the end. So I won't go into all the details in this talk, but if anyone wants this paper, I can share this. So these are the kind of results you can get with pulsing. So what are the challenges here? There are still challenges. So for example, generators can misfire. I think this is less of an issue on modern generators, but if you have older generators, there are issues where it doesn't do all the pulses that you expect it to do. So because of these misfires cause some issues. So as I showed, the ion energy is sensitive to the duty cycle. So if you misfire a pulse, so if you misfire, so if you don't, if you miss a pulse, for example, you're effectively changing the pulse frequency. Um, um, and if the shape gets distorted, either from the RF transmission line, or matchbox issues, what happens is how do I word this? So if the duty cycle changes, so the effective duty cycle delivered to the tool can change. Okay. So what needs to happen is you need to be monitoring like if you develop a process at a certain duty cycle, you need to monitor, is that duty cycle actually being delivered? Because the energy is so sensitive to that number and the flux. So, if you develop a process at 50% duty cycle, maybe the tolerance of the process is plus or minus 2%. But outside of that, you now have a totally different ion energy and ion flux compared to what you develop. So you're not going to get the rates you expect, and you're not going to get the material properties that you expect. So it is important to monitor, are you actually delivering these? In terms of misfires, we do have a product called the Alpha, which can monitor those. In terms of monitoring the pulse frequency and duty cycle, the Alpha and Octa products, the VI probes we have, can monitor those in real time. And the other challenge is related to matching. So if you're pulsing, and if you look at those previous diagrams, where is it? This is the plasma evolution. So the plasma impedance is changing quite a lot, and this could be at 1,000 times a second. So a mechanical matchbox cannot keep up with this. So how do you match? At what point do you match? Should you match here or here? It's obviously easier to match for longer. If you match at this point, you're probably matched all along here, but you're unmatched here. That's going to cause issues with reflected power on the generator. It's going to cause standing waves to happen, which may cause voltage spikes, may cause arcing. So matching is also difficult. But if you want to tune your matchbox and like see at what point are you matching and not matching, we do have time resolve features available in our VI probe, so you could take a look at that if you wish. There are other advantages to pulse RF not mentioned here. So, for example, they can be used to control charging, how wafer level charging happens, but it's kind of outside the scope of this talk. So, tailored waveform. What about tailored waveform? What is that? Earlier on, I showed these examples. So this is from a tool where you change the ICP power, you see these different results. And if you change the bias power, you get these different results. So I want to show you some tailored waveform results from the same tool type. Okay. Again, this is all published work. Ask me for the paper if you wish. This is in an Oxford Instrument Flexal tool. And so if you look at, if you apply RF to a bias, so this is an example here. So 1 power, you're getting this blue wave. As you increase the power, you get higher voltage. So you get this yellow-orange wave being applied. And then if you have a look at the resulting distribution function, with the smaller power you get this, and with the higher power you get this. So like I've shown you previously. But if you don't have to apply a sine wave, okay? So what happens if you apply power with a specific shape? So in this case, it looks kind of like pulse DC. You have like this narrow spike, and then you have a ramp down. And by applying this shape, you actually get these very narrow ion energy distributions. So this, this firstly gives you more control over the etch rate, because you're now dealing with a more singular, like a much narrower distribution of energy. So you're dealing with one etch rate from that energy, as opposed to multiple etch rates across a broad range of energies. And again, as you increase the power may be hard to define here, but as you increase the power, you can increase the energy. There are ways then also to to modify the flux by playing with this. Okay. In this case, the base frequency was about 100 kilohertz, something like that. With the benefit of using low frequencies, is you can use this to achieve much higher energies. Okay. So this is probably the way to go in the future for how to achieve ion energy control. Not just for high energies, but also low. So you may want to produce a plasma and have ions that are at the 3 eV, 4 eV, 5 eV mark. Like if you're doing atomic etching or something like, or deposition. You want to have very, very fine control over the energies. So this is the way you'll need to go. So I think tailored waveform and atomic layer processes are going to go hand in hand over the next 5 to 10 years. Let me show. And actually, yeah, for these same results, this is showing the ion energy and ion flux behavior here. Let's go forward. I mentioned this, the idea of the different energies being important. So this is the etch rate per cycle of atomic layer etching process. And then there's some sort of threshold at which you start doing something. There's the atomic layer etching window where you have the self-limitation, and then you get to the point where you have physical sputtering. So if you have a broad distribution, you could have parts of the distribution sitting in each of these windows. So by going to a narrower distribution, you can sit comfortably in one of the windows at the rate that you want, as opposed to having contributions from multiple different windows. Okay, so this is why it's important for atomic layer processes going forward. Okay. Just some other examples, like applying the square wave to get different peaks. Here's another example, like again, these sort of unusual waveforms to get these distributions. Let me show you one other example. So this is playing with, if you want two different distribution peaks, you can actually play with that as well. So if you want to do this in your lab, you can just do this with a waveform generator or power amplifier. But then there's a question of matching. So let's talk about the challenges. I should mention, obviously, all the data that have been shown so far has been measured with, the impedance RFEAs. So if we look at tailored waveform challenges, one thing is the generators are relatively new, and I think tools aren't really developed yet to use them. So there's the Advanced Energy EBOS. Trump-Fullinger seem to have something along these lines. Also, Eagle Harbor Technologies are developing these technologies as well. They have a publication on their website, which is quite nice. So one challenge is it's not yet, mass available for the industry, but I think this needs a lot of attention in the near future. We also have the same question with pulsed RF. How do you match a complicated waveform? There was a talk at GEC a few weeks ago, and a question came up in one of the presentations of, can matching be ditched? Can we go direct from the generator? Can you develop a generator that goes direct to the tool? So if you look up Alex Patterson's talk at the GEC, they talk a bit about this. And then, like also with pulsed RF, what's actually delivered to the electrode is what matters. So with pulsed RF, what's output from the generator, which are these nice, clean, rectangular waves, and what makes it through the matchbox, and what makes it all the way through the transmission line to the wafer surface in this non-50 ohm region, that it can get quite distorted. And the same idea is going to apply, obviously, with this tailored waveform. You can think of it as a multitude of different frequencies added together. Okay, so each frequency has to be matched independently. So, which means, so that's one difficulty, and also, what we have to know what's delivered to the electrode itself. Okay, so we can make corrections depending on, like maybe the transmission depends on temperature. So just so you know, our impedance octave suite can measure tailored waveforms in real time and give you the waveforms back. So for the closed-loop feedback control, do speak to us about that. We're running a little over, but I still want to touch on two topics, so I'll go quite quickly to them. The two topics are ion angular distribution measurements and radical etch measurements. So I want to touch these. So I'll overrun 4 or 5 minutes before we're going to Q&A. Just quickly, before I can talk about these, I do have to introduce the instruments because it won't make sense if I don't. So you may be familiar that impedance has these RFEAs, the Semion, semi-PDC, quantum, and other things. And this is how you install one on the tool. So you can see a ion energy analyzer in the tool here. You can see this is the vacuum feed through, and you see the data in the background. So I think many people on this call is familiar with what we have. And this is sort of a cross section of the sensor. You have these nickel meshes, you have various different grids. We apply different voltages to them in order to discriminate what's the ion energies. And then by measuring the current and the transmission of all this, we can get the ion flux. Okay. So let's move forward. And I've already shown you some data examples of this. So how do we measure ion angular distribution? Okay. And I think that the concept is fairly straightforward. This was actually demonstrated again by our attendee, Gilles. A number of years ago, he published a nice paper showing this. But the idea is use capillary plates to mechanically restrict the ion angles allowed to enter the RFEA. Okay, so this is a screenshot from his paper, and this is a capillary plate. So what is a capillary plate? So it's a thin flat disc, usually made of some sort of glass, and there's loads of micro scale holes drilled into it. So for example, this could be 1 millimeter thick, and it has a big array of 5 micron wide holes drilled into it. So what this results in is that this plate, all these holes, have an aspect ratio of 200 to 1. You know, so it'll be the 1,000 microns thick divided by the 5 microns diameter is 200. Okay, so that'll be a 200 to 1 plate, but you can get these made in all sorts of different dimensions. And what happens is you can measure an ion angular distribution where there's no plate on top, and that has a 45-degree acceptance angle. But then as you place different plates on the top with different aspect ratios, you can measure what the ion energy distribution function would be like after it gets to the bottom of that trench, of that depth, okay, or that aspect ratio. So, you know, I mentioned there, I do need to show one more step to this, so bear with me a moment. But you can see here different ion energy distribution functions and different depths. And you can see, for example, as you got narrower and narrower acceptance angles, fewer and fewer ions made it to the bottom of the trench. So remember, the area under this curve is the ion flux. So in this case, the ion flux is decreased by more than a factor of 2. And in this experiment, it's decreased by a factor of 4 nearly. So this is actually a measurement of what the etch rate is as a function of depth, if you think about it. You can also see that low energy ions are lost faster than high energy ions in these cases. So what's the concept to measure the ion angular distribution function from this? So the idea is you would place different capillary plates over different sensing elements on one of these arrays. So when you have no capillary plate, that's giving you information of ions less than 45 degrees. And then if you apply different capillary plates with different angles, you basically can build up a histogram, you know. So what you do is you have all these different angular plates all around at once. And by subtracting, so if you subtract, so you get the 45-degree bucket. If you subtract the 10 degrees, that tells you what's between 45 and 10 and what's 10 and below. And then if you subtract the 5, that's going to then split from 10 to 5 and 5 and below. And you get the idea. So you build up a histogram. And by the end, you can be getting down to very small angles. And then you can get a distribution of, you know, where all the ions are at. So the final result here is an ion angular distribution function. Now, I don't have an example to show here, I'm afraid, but we have tried this before, and you can get fairly reasonable results. Like you do see a Gaussian style distribution when you use this technique. And this can be done just with the existing, you know, RFEAs out there with just the addition of capillary plates. Okay, the last topic is radical monitoring, which is going to be very important. This is short, it's just 2 slides. So radicals, you know, they're uncharged atoms with unsatisfied chemical bonds. And these are more numerous than ions in gas flow discharges because, you know, the energy for excitation is typically smaller than what's required to ionize or whatever, okay? And radicals also have a much longer lifetime in a plasma because the ion is pretty much always neutralized if it has a collision with a surface, but the radical can actually hit a surface and come back on. So you can have like a high population of radicals that are long lasting. One notice that the reaction probability does depend on substrate temperature. So what's the concept? So this is just a concept. So what happens if we use a coated quartz crystal microbalance? So the idea is that the absolute change so with a quartz crystal microbalance, the absolute change in resonance frequency is proportional to the mass of the crystal. Okay, so usually they're used for deposition. So as you deposit, the crystal frequency changes, and as the crystal frequency changes, there's some models that turn that into, layer thickness and deposition rates. But what would happen if you pre-coded the quartz crystal microbalance with the material you're interested in etching? So then you can monitor the frequency change in reverse. Okay, so you could be using it to monitor etch rate. Now, obviously, if you place this on a substrate, you have ions present, right? So we do have a sensor called the quantum RFEA, and this is built like this. It has a quartz crystal microbalance on the bottom, and it has the RFEA grids above it. So you can actually repel the ions or let them through. So we think in this case, if you repel the ions and monitor the resulting deposition rates, or the resulting, I suppose it'd be etch rates, and that could be a way of live monitoring what the radicals are doing. Okay, so it's just a concept, but I think it will work because live radical monitoring is currently, as far as I know, not achievable. You can only apply it to put in a substrate, put in a product, and see what happens. So yeah, and the data would look something like this. You get different slopes depending on whether the ions are blocked or the ions are allowed through. I'm going to skip ahead because we're right at the end. Just know that we do have sensors also for pulse DC monitoring, for time resolved pulse DC monitoring. So in summary, we went through some of the challenges of the semiconductor industry, particularly with surface interactions, and how we might be able to help in looking at those. So I will answer any questions people have, yeah, thank you very much for attending. So there is the Q&A section. So I can see all the Q&A and I'll read them out. Can you please share this presentation? Yeah, no problem. So the presentation, I forgot to mention at the start, this presentation will be shared with all the people who registered for the talk. So you'll all get this afterwards. Ben is asking, how is plasma charge dissipated in the CCP with grounded bottom electrode versus RF bottom electrode? Okay. Let's go through that. So one thing that you need to think about, Ben, in a CCP, so it takes me too long to scroll all the way, there's like 60 slides, so I won't scroll all the way back to the diagram of the CCP, but the idea is, whenever you're thinking of how charges are behaving in a chamber, just keep in mind that even in a CCP, there's not two electrodes, there's three. Okay, so you have the top electrode, bottom electrode, and the walls. So you must never forget that the walls are there. So just keep that in mind when you're thinking about charge balance. I know with modern chambers, there's like anodizing of the walls or insulating of the walls, or something can happen for various reasons for doing that. In a grounded bottom electrode, yeah, charge just gets absorbed. In an RF biased bottom electrode, how is charge dissipated? How do I answer that? Because it kind of depends. Like if you have a bare metal electrode, it's fairly straightforward, right? It's like AC in a wire. If you have an electrostatic chuck, it's a bit more complicated because you normally have like a ceramic layer or something, right? So I'm not entirely sure. I'm mostly thinking about how charge balance happens with the electrons and ions hitting the surface. I don't know. I think Ben will have to answer that in an email. Let me scroll down. Are there other methods to detect the radical energy? I'm not entirely sure. Like it's something I'm trying to think of. Like how can we do that? Because what I've mentioned here is really just etch rate. It doesn't separate out the energy and the flux, right? As far as I know, there's no method because all the methods of diagnostics that are like listed here are all based on the thing having charge. The only thing I would say is the radicals we can assume must have the same energy as the neutrals, right? Or like their energy distribution. So if there's ions present, and assuming a charge exchange collision doesn't happen if it's just momentum transfer, the ion energy, the gas distributions will maybe have the radical distributions will maybe have a peak related to ions colliding with them, and then a peak related to the gas temperature. and then you have to take into account collisions. So that's my first order guess. Do you understand correctly that you compare your measurements to models? If so, which models do you compare? Most of our clients would actually have some sort of model that they're comparing. So in all the papers I mentioned with tailored waveforms, those papers do contain models so they can predict what the waveforms look like, if that's what you're asking. So it's going to, depending on exactly what you mean, it's a case-by-case basis. But I'll make a note to contact you after this to share the papers, and you can have a look at what models people use. They always talk about, whatever COMSOL or their own pick model or whatever. More questions? Could you please spend a bit more time presenting the time-resolved IED measurements? Yes, I actually have I did a presentation primarily on the RFEA measurements actually about this time last year, not a few months ago. I could probably share that talk. It does have more information on these time resolved measurements like what are shown here, like these things. So these are ion energy distribution versus time on a microsecond time scale. So if this is what you want, yeah, I have a presentation on this. I'll share that with you afterwards. No problem, Alessandro. No problem, Oleg. Okay. Are there any further questions? We still have 4 minutes left if anyone wants to put one in. More info for ionics, yes. So for a long time, Impedance has been working on an ion energy wafer, which doesn't have any wires attached to it. We have made very, very good progress. We've patented a lot of techniques. We have prototypes. So the anonymous attendee, email me offline and I can host a presentation on where we're at with this. But it's still not released as a product. There's still like the concept is proven, but the reliability is a challenge. That's where we're at the moment. So we need to make it reliable before it'd be acceptable to release to the public. Okay. Any other questions? No. Be interested. Okay, sure. So yep. So you can email us. I'll put up the next slide. You can info@impedance.com or at thomas.gilmore@impedance.com. I'll get back to you, answer whatever questions you want, or hold a private meeting. Not an issue. So if there's no further questions, let's leave it there. I'll get back to the people who asked me questions, and thanks very much for attending. In the next couple of days, we'll send out the presentation. Okay. Thanks very much, everybody.